Thank you very much. So I will talk about stable models for modular curves in prime level, and this is a joint work with Bas Edixhoven. Actually, this is a work in progress. I mean, we still need to write down the details with care, so okay, I'm pretty sure of what I will tell, but I'm the only responsible for the mistakes I shall make, of course. So let me start with a quite familiar picture, I think, which is that of the special fiber of the Linear-Rapoport model for x naught of p. So x naught of p is the famous modular curve, which has been discussed several times since the beginning of this week, and in particular in Samuel Lefront's lecture this morning. So this parameterizes isomorphism classes of elliptic curves endowed with a group of order p. And this has a well-known integral model described by Deligne and Rapoport, which says that over Zp, of course this is a generically smooth curve, which at p becomes singular and has the following shape. So there are two irreducible components which are J-lines, so copies of P1, and the two intersect in a certain number of points which correspond to supersingular J invariants in characteristic P, and the set of those supersingular invariants I will denote by curly S during all my talk. And there is a very natural modular interpretation of this fiber, because what is to give an elliptic curve and a P isogeny in characteristic P when, generically the elliptic curve is ordinary. And then on such a curve in characteristic P, one only has two P isogenies, which are the Frobenius and the Verschiebung, the dual isogeny to the Frobenius. And it is also well known that the Frobenius is a radical isogeny and the Verschiebung is étale if E is ordinary. But it is the definition, one definition of an ordinary elliptic curve. Okay. And okay, so if you want to describe the isomorphism class of an elliptic curve in characteristic P, well, you first have to describe the isomorphism class of the elliptic curve itself. So you have to specify its J invariant, and then you just have to say, well, I want the P isogeny to be either the radical one or the étale one. So I have to choose which component, which J line I am on. One is devoted to the radical guys, and the other one to the étale isogenies. And of course, there is one case where you cannot distinguish between the two, and it is precisely when the elliptic curve is supersingular, in which case the Verschiebung and the kernel of the Verschiebung and the Frobenius are the same. So this explains why one should make the two components cross at supersingular J invariants. Okay, and this This model, this integral model of the linear Rappaport, has the very nice property of being semi-stable, and actually stable if the genus is not too small. If there is at least 3 crossing points, then it is even a stable model. So just to fix things, a relative curve is semi-stable if each geometric fiber is reduced and the singularities are ordinary double point. And a relative curve is stable if it is semi-stable and it is projective and connected, and the P1s that occur cross the other component at least 3 points. So it's a more technically demanding condition, but the key point for us will be that the singularities have a good shape, and in all the cases we will meet, the curve will be will be stable. So we will not distinguish a lot between the 2 properties. So unless the level is very small, the semi-stable objects are stable. Okay, so this is a stable model, generically. And this is interesting because it allows you to describe quite precisely the neural model of the Jacobian of such a curve. So let me recall that if A is an abelian variety over say a number field, or the completion at some prime of a number field. So up to make a finite extension of K, one can assume that the neural model of A over F over the integers OF of F. One can assume that this a priori semi-abelian scheme, this scheme is semi-abelian. So at residue field, one has the exact sequence describing the reduction. So we know that this guy is the extension of an abelian variety by a torus. So there is a torus here. And I don't know. And we can describe, in the case A is the Jacobian, so this is for the 0 component of the fiber. So if A is the Jacobian of some curve C, and C is a semi-stable model for C over OF, then the toric part, so this is a torus, this is an abelian variety, then the toric part Tk, or at least over K bar, is just a power of the multiplicative group over K bar to the rank of the first singular homology group G, where G is the dual graph of the spatial fiber of C at K. So in particular, in that case, the dual graph is quite simple. It is what is called usually a banana graph. You just have the two J lines, and you have a certain number of edges between them, which is in bijection with the crossing points, so the super-Lagrange invariance. So it means that the toric part exhausts all the fiber. So the Jacobian J naught of P, which is by definition the Jacobian of X naught of P, has purely toric reduction at P. And is an abundant variety elsewhere. Okay, so we understand quite precisely what happens for X naught of P. And now we can ask the same question for the other interesting modular curves in prime level. So what about the other modular curves associated with maximal subgroups of GL2 of FP. And we know, and this was recalled by Samuel Lefourne in his talk this morning, that they are of two types, apart the X naught of PKs. So they are the XS plus P split Cartan, normalizer of split Cartan, curve, and the non-split curve and exceptional curves, which are curves associated with exceptional subgroups which are of lesser arithmetic interest, so we will not discuss them, even if our methods can also apply to them. But we will focus on the two main other families. And well, I think it's well, my goal here is to describe semi-stable models for those guys. And the motivation for that is, well, first, I guess modular curves are objects of daily life interest, so it is natural to clean up the situation for them. And there is also an arithmetic motivation, because in, I think, all works on the rational points of those objects, the precise understanding of the spatial fiber of those objects and correspondingly of the type of reduction of the Jacobian plays a role. So we do need to understand spatial fibers of those guys, and this is in particular the case in the very exciting new work that Samuel discussed this morning. And when you look at the work of Balakrishnan, Dogra, Müller, Teutmann, Vonk, I think I did not forget anybody, about the development of Myung Kim's ideas to quadratic Chaboty and its application to the study of rational points of X non-split 13. Well, you see that they do need at some point to know that this curve has a good reduction everywhere, and in particular at 13. And well, I understand that it is not a crucial hypothesis for them to know that the reduction is good at 13, but at least they need to have some control on the type of reduction of the curve everywhere. So, I mean, this provides another motivation for this description of semi-stable models for those. So here is the result I will try to discuss. So for the curve x split plus p, one can describe a stable model or semi-stable model which has the following shape. So there is a dichotomy depending on the class of P mod 4. So if P is 1 mod 4, there is there are three vertical components. So there is one which is just a projective line. And there are two Igusa curves, or actually quotients of Igusa curves. And if P is minus 1 mod 4, then we have the same P1 showing up, and there is only one quotient of Igusa curve. And there are there is a certain number of horizontal components whose number is the same, sorry, on the right and on the left. So there is cardinal of S horizontal components, which are explicitly described as hyperelliptic curves. I guess I will give some more information on that at the end. And we also know the multiplicity of the intersections, so we basically know everything on that fiber. And from this description, we can read the toric rank of the spatial fiber of their Jacobians. So if P is 1 mod 4, then the toric rank is 2 cardinal of S, which is, if you prefer, so minus 1, to the genus of, twice the genus of X mod of P. And if P is minus 1 mod 4, it is only once cardinal of S minus 1. So this is something which is linear in P, and the genus is quadratic in P, so there is a small part which is toric, and most of the Jacobian is abelian, but there is a small toric contribution. And so this was more or less known, I think, those models for the split curve. And as for the non-split curve, I think this is newer. We have something which is, yes, quite similar. So again, there is a dichotomy. So either P is 1 mod 4, is it? Yeah, it's the correct order. Or P is minus 1 mod 4. And in that case, we have two vertical components only. Again, we have Igusa curves, or quotients of Igusa curves. The same number of horizontal components. And in that case, when P equals minus 1 mod 4, there is only one vertical component and a certain number of horizontal ones, which again are hyperelliptic curves, which are given by explicit equation. And in that case, the toric rank is something which is linear in P, and here it is 0. So I think we see a rather interesting geometric object appear. This guy is a curve whose dual graph clearly has no homology. His dual graph is just a kind of star. So it is a curve which has bad reduction, but the Jacobian of this curve is an abelian scheme when you have made a sufficiently large base extension. So in some sense, it is the Jacobian has good reduction as an abelian variety, but has bad reduction as a polarized abelian variety, because if you wish, the theta divisor of this Jacobian is irreducible except in the bad fibers, where it breaks down into a certain number of irreducible components. So, okay, those objects exist, and this is an example of such guys. Good. Something I will not discuss is that we also have a good description of the inertia action on those models. So we can actually recover models over Z for those objects, which fit with the intuitive modular interpretation we have for those moduli problems. I shall also say that, I say that I'm only considering prime levels, and this is a strong limitation. Perhaps not for arithmetic purposes, because when you know things in level P, you're happy usually. But geometrically, we cannot describe what's going on for level P to the n when n is larger than 2. And this is really due to the method we use, because at some point, I hope explain that at some point. We do need to have some constraint on the multiplicity of the components which occur on those models, and this is not satisfied when the level is divided by, it's divisible by p squared. So we cannot treat the case of x non-split p of p squared or p cubed or something, but there is this work of Jared Weinstein, which uses the language of perfectoids and things like that, which is able to describe a stable model for x of p to the anything, or x of p to the anything is the curve associated with the full p to the n structure. And so I think it should be used, but yet it seems that the work of Weinstein is not able to describe as precisely the spatial fibers, because he says he cannot precisely compute the multiplicity intersection of the irreducible components, for instance. So, okay. Perhaps we have here information that we cannot yet obtain by other means. Of course, there are some small also Arakelov outputs you can get from such a description. For instance, you can describe the Green-Jean function on describing the theta height on those curves by knowing that kind of dual graph. And, okay, I will not enter into those details here. So this is something, the result is a kind of technical perhaps. So the method consists in computations. But I will try to give some flavor on the ideas which are used for performing those computations. And in particular, I will try to give some flavor of what we use, which is the Katz-Maser model for x of p, and how it can be understood by with the modular intuition. How do I? No. Yes. So let me first try to give an idea of the modular model of Katz-Maser. Then I will try to explain how Edixhoven computes from Katz-Maser model a semi-stable model for x of p, the modular curve associated with the full torsion in the full p torsion. And then I will describe how one can take quotients by suitable subgroups of GL2 of FP to obtain those models. So cats and lasers model for x of p. So we need to introduce what is perhaps the main idea in the theory of Katz and Maser in their book Arithmetic Moduli for Elliptic Curves, which is that of a Greenfeld basis. So let me give a rather vague definition. So we fix an integer, a positive integer, n, and a relative elliptic curve over S, which is any scheme for now. And we say that a gamma of n structure for E is the datum of a group morphism phi from Z mod nz square to the group of n torsion points with values in S of E, such that we have an inequality as divisors between that object and that one. So this is an equality as divisor and actually as effective Cartier divisors. So an effective Cartier divisor is just a flat divisor, such that its sheaf of ideal is an invertible sheaf. And so you just look at the images of the points by your phi. So it defines it defines a section, and so it defines a divisor, and you take the sum as divisors of those objects, and you want it to be equal to the group scheme E of n. So when n is invertible on S, this is nothing different from the usual definition of level n structure. But when n is not invertible, in particular when n is p and S is a FP scheme, then you do have something which is new and which is the good way to define a full n torsion structure. Because, okay, let me recall that if one has an elliptic curve over S, which is an FP scheme, then we have the Frobenius isogeny. Perhaps I would call it Frob, as I did in the first blackboard. So you have this isogeny, and so there is again the dual isogeny to the Frobenius, and then Frob Verschiebung is étal if E is ordinary. So what's going on? Well, if in that case okay, I should introduce another definition. We call P and Q, which are the images of the canonical basis of the Z mod nz squared I have here, we call such a set a Drinfeld basis. A Drinfeld basis for E of n, and and with that terminology, we see that 0p is a Drinfeld basis if p is a physical point, is a point of physical order p, and in the case E ordinary, and 0, 0 is a Drinfeld basis if E is supersingular. So that just means that in any case, we don't have enough p points to have a usual notion of p structure, but yet if we can describe all this group scheme, even with its nilpotent structure, with 2 points here, we're happy, and we call it a Drinfeld basis. And so, in any case, we have bases where one of the elements of the basis is the zero section, which is a bit strange, but which is the way it works. And in the supersingular situation, of course, it is even worse because here the 2 elements of the basis are the same zero section. So that's the concept of a gamma n structure in the sense of Katzenmaser. And another terminology I need to introduce. It cannot be moved at the same time. So okay, this one. Okay, so with this, I need to introduce the notion of, to recall the notion of Igusa curve. So an exotic, this is not very important, but this is the right terminology, Igusa structure is of level P, is the datum of some point P in E, such that P generates the étale part of the elliptic curve when it exists. Okay, so this is the an object which is similar to the modular curve x1 of P, and characteristic P. And then there is a theorem of Igusa which says that such a structure is representable. So if, to be precise, if K over Fp is a perfect field, then the moduli problem Igusa at P and some rigidification. So P is, for instance, gamma 1 of 3. So this is just a technical thing, so I will not develop on that. So this is representable by a curve, which I will call M of ig P curly P. Okay, so we can represent Igusa structure. And now we can come with those definitions to the description of the model by Katz and Maser for x of P. So let x be the curve associated with the full P torsion gamma of P in the sense of Katz and Maser and some additional structure I won't explain. Let this guy be the compactified moduli scheme parametrizing triples E, phi, and alpha. So phi is, this is a gamma of P structure. And this is a P structure, but again, it is just here to make life simpler. And then when we have such an object, there is a natural tool which comes into the picture, which is the veil pairing. So there is the veil pairing, EP, which goes from EP cross EP over S to the pth, the P roots of unity, and which to such a triple here associates the pairing of the image of a Drinfeld basis. And this shows that the curve, this guy, this x, is naturally defined over spec ZP. So there is the structural morphism given here, but this factorizes through spec of zeta p because of the existence of this veil pairing. And so it's more natural perhaps to extend basis to z of zeta p. And then we see that this object decomposes into a certain number of irreducible components, which I will denote by xi. And those are the objects on which Katz and Maser give a description. No, sorry. Okay. And I want to press. Yeah. Okay. So I call xi, which is m gamma of p zeta pi canonical p. So it corresponds to this is defined over z of zeta p, and it corresponds to triple such that the veil pairing of the canonical Drinfeld basis is just zeta p to the I. Okay, so this is something more natural to consider, because then we have a bunch of copies of xi, which goes to the x introduced here. And if we take the normalization of the right-hand object, then the natural map becomes an isomorphism. So it is easier to study those objects, the xi, and with them I can describe a Katz-Maser model for each of those. So Katz-Maser model for each xi. This is something like that. But this time, one has p plus 1 So there are p plus 1 irreducible components. And they again cross at supersingular points. And each of them, each component is an Igusa curve. They are parametrized by P1 of Fp, and so on the union of the xi, we label them as ig I L for I L in the set Fp cross times P1 of Fp. And okay, here I can give a modular intuition on that fact. Why should it be so? So first, yeah. Why should it be so? Well, why is it to give a full gamma of p structure in characteristic p with the notion of Drinfeld basis I just introduced? Well, in generic case, on an elliptic curve, you have again the kernel of the Frobenius and the kernel of Verschiebung. So first, you have to choose within z mod pz squared what will be mapped to 0 via phi. And then, once you have done that, you have to choose what will be your point of physical order p on the elliptic curve. So, concretely, why this shape? Well, if E over S is ordinary and phi is the gamma of P structure, then to describe phi, one needs to, it amounts to give a line L in Z mod PZ squared, which is the kernel of phi, and then describe the isomorphism between Z mod PZ squared divided by L and the kernel of Verschiebung, which is isomorphic to Z mod PZ. So this gives an Igusa structure. So that's the reason for you have, for each line in pz mod pz squared, you have a component which is an Igusa curve, and they all meet in a supersingular invariance for the same reason as for x naught of p. Okay, so now from that model, Edixhoven has computed a stable model, because this is highly non-stable. As you can see, the crossing points do not have the right appearance. So Edixhoven computed a stable model for the xi. And I don't enter into the details here, but let me just say that it is obtained by blowing up at singular points in order to obtain a normal crossing. Then you have to make a base extension, which corresponds to basically to the multiplicity of the new components you have obtained by blowing up, and then you normalize. And this is doable only when the level is prime. This is the technical part which demands the level to be prime, if we don't want to use analytic geometry. And so the model is just something of this shape. So here you have the Igusa vertical components, which are there, but they are pulled apart. And here you have new components which are obtained by blowing up, and which can be described quite very precisely with equations because of the blowing up computation. Okay, and now we will work on that model, and we will make a quotient by GL2 to obtain a model for those curves associated with the subgroups of GL2 of Fp. So to do that, we need to describe the action of GL2 of Fp. Well, we can again do that modularly. So if we have an elliptic curve with basically a gamma of p structure phi here, and if we have an element G in GL2 of Fp, then what is the modular interpretation of the action of G on this object? You just compose the Drinfeld structure, or the gamma of p structure, by G. So now, what happens with the veil pairing? Well, it is known that when you make the action of G on the basis of the Petersian, the veil pairing is raised to the power determinant of G. And so it shows that G is an isomorphism between the component ig_il to ig_i times det G times G minus 1 of L. Because now it is clear what will be the kernel of phi if you multiply the Drinfeld basis by G. So we also have a description of the this way. Good. We have a description of the action of GL2 of Fp on the vertical components, but we also can prove a very precise action of G on the horizontal components, which appeared on the stable model of Edixhoven. And now, using that, we can just take the quotient to obtain our model for the non-split curve. And this is a small computation basically in group theory to obtain a model by taking quotient of some subgroup of GL2 of Fp, which is non-split Cartan subgroup, which is made of two vertical components and some dreamfold components. And this is done just by reading, by computing the quotient of our set of parametrization, so Fp cross times P1 of Fp, mod out by T tilde, the non-split Cartan subgroup. This is just a small group computation. And of course, we have to make some more work to compute what become the horizontal components, and also what happens with the intersection points, and also to describe perhaps the inertia action. But this is another story. And we see also that the Atkin-Lehner or the Fricker involution, which corresponds to the, not to the non-split Cartan subgroup, but to its normalizer, permutes the two vertical components if and only if P is, so this is -1.4. So again, this is just a bit of group theory. So this explains those models. To be completely explicit, let me give some equations, some instance of equations of the horizontal components. So they are just given by y squared equals x times x to the p plus 1 mod 2 plus something. And this is in the generic case, or we can make 2e if we want to describe all the horizontal components. But this is very, very concrete. And in the remaining 3 minutes, perhaps, I will just focus on the concrete case of X non-split 13, which was studied by Balakrishnan and others, and to which they managed to apply their new Chaboty method. And I said at the beginning that they needed their curve to have good reduction at P, which is here 13. And we know also, by other arguments, I mean by a result of Bourdieu-Baran, that in level 13, the two curve X split and X non-split are isomorphic. And this sounds problematic because it is quite clear from this drawing that first, those curves don't have good reduction, and two, the two curves are not isomorphic. I mean, the combinatorics of the graphs are not the same. But yet, it works because of the following reason. So for P equals 13, so here we have X split plus P of 13. So in my case, it is just one horizontal components, one P1 and two Igusa components. And for the X non-split plus of 13, we have one horizontal components and two Igusa components, or quotient of Igusa. And so, again, those curves are clearly not isomorphic and don't look having good reduction. But what I said at the beginning is that I will not bother about the difference between stable and semi-stable is not true here. I mean, it's not possible here because here, as P is very small, the combinatorics of the dual graph is quite spatial. And here it is not, it is stable, it is semi-stable but not stable because to get something stable, again, we need the P1 to intersect the other components in enough points. And here, this P1 intersects the other irreducible components in only one point. So to get something semi-stable, we need to contract this first component. And it occurs also that this is very rare, but in that case, the Igusa components have genus 0. So we can also contract the two guys here. So we are left with that horizontal component And the same thing occurs here. I mean, those two guys, again, have genus 0. So to get something stable, we contract them. And we also reduce to one irreducible components. And then genus compute, I mean, explicit equations show that those two horizontal components do, I mean, are really isomorphic. So it is true that both the curves have good reduction, and it does not contradict at least the fact that they are generically isomorphic, which is known by other means and by other people. So I think that concludes what I wanted to say, and I thank you for your attention.
Okay, are there any questions? Yeah. Sorry. Thank you. From the way you build those models, it seems to me that correspondence that exists between those two modular curves, which is known to exist generically, carries a work to those models. But can you see that explicitly?
No, I think I cannot. And I mean, it is true that all the irreducible components here, I mean, all the ones that have some modular interpretation can be, I mean, related from one curve to the other. But I don't see how you can understand the link when you think of the modular interpretation of the points of those two guys. I mean, not thinking component by component. But it's not completely clear to me. One has to think about it.
To make the question a bit more precise, of course, you start from the model for x of p and you derive by taking quotient. So obviously there is a correspondence which goes to one model to the other because you go up and down simply. Can you actually see something better than that? Because this is certainly not the only correspondence between two curves. There might be a more natural one that you can see on those models.
I have to think about that. I don't know. That's an interesting question. But
any other questions?
Can you say something about the chain of inertia?
In few words, I'm not sure, but yes, I mean, what I can say is that when you compute the quotient of all that guys by the action of inertia, for instance, you see that in the non-split case, of course, first you have to, I mean, when you go down to Z, the horizontal components just contract, and then you are left with the components which do have a modular interpretation. And you see that they are switched by inertia when they are not by the Fricker involution. So it means that over Z, the non-split Cartan curve has the expected shape of only one big component with multiplicity p plus 1. And this amounts to the fact that you gave a modular interpretation of the non-split Cartan structure in terms of necklaces, and that in characteristic P there is basically one necklace. That's all. So that explains the fact that there is only one irreducible component in characteristic P, and this is recovered by the quotient by inertia.
Any other questions? If not, then thank you.